So let's talk torque for a minute. A torque is sort of a rotational force. If you've ever had to take the lug nuts off your car tire to remove a flat, you put a wrench on there, some kind of wrench, right? And then it's righty-tighty, so lefty-loosey. So if I want to take it off, I go this way, right? And so what I do is I exert a force, F, at some distance along the handle, R, right? And so the distance from the rotational axis to the point of action of the force is called, is R, and we kind of call that maybe the moment arm, right? It's sort of the distance leverage you have with that force. And so the torque has to take both of these things into account, because the longer the lever arm, the better an opportunity I have to cause the rotation. And so if I have, let me reverse this. So if you're having a hard time getting your lug nuts off your car, you have a few options, right? So here's my wrench. Not as pretty a one, I hurried it. Now to take it off, I want to go this way. And so if I'm having trouble taking it off, one of the things I can do is just stand on it. This is what I did with my car one time. I couldn't get the lug nuts off, and so I put my foot, I turned it the other way, put my foot on it, and I stood on it. And so I got a much bigger force here. Right? Same R, but a much bigger force. What do you think happened? That's right, I broke the lug nut off. The nut didn't release from the screw just broke off, the bolt just broke off the car. And so then I had to do another one. So I tried to take the next one off, and I broke that one off too, and so I got my car towed. That's how that went. But if I don't have a situation where I can stand on it, another option I have is to use what's called a cheater bar, right? And here's what a cheater bar does. So now I'm going to draw my nut over here, right, like this. Here's my wrench. What a cheater bar is if I can't get this thing to turn this way, F fails, it won't move, right? I can take a pipe and slide it over the end of this wrench like this, and now it goes all the way back to here. And now what I've done is I've increased my radius, my moment arm, much larger, and now my force might be able to move it. And so these are typical sort of torque type situations where you're loosening a screw or doing something like that, right? And so what matters, there are several things that matter here. Let me go back to my first drawing, right? Right. Not only does the force matter, but also the distance matters. That's what we were just talking about. It turns out what else matters is this angle here, or however you want to measure the angle. This angle is really the relevant angle. So let me say it that way. I'll explain that in a minute. So for example, if I was silly, I might point my force this way, so just pushing on the wrench, and we can clearly see that that's not going to take the nut off, right? Or if I could somehow, if this was like a socket, I could pull. If it was a wrench, it would just come off. But if it was a socket, I could pull and make my force that way. And I think we all can see that that wouldn't turn the nut either. And so the angle between F and R matters. And so it turns out the definition of the torque, at least its magnitude, is the moment arm times the force. Sorry, the definition of the torque. We use the Greek letter tau for torque. It's the moment arm times the force times the sine of the angle between the directions of these two guys. And so R equals distance from the rotation axis to the point of action of the force F is the force, and theta is the angle between the direction of R and the direction of F. And so in our little example with the nut, right, here's my not very good. Right, here's my nut, and here's my wrench. Right, something like that. This is my R to where the force is acting. This is my F. And so the direction of R is this way, and the direction of F is this way. And so the angle is from R to F, like that. That's what I would call my theta. It turns out it doesn't matter which of these two angles you pick, because even if F is this way, the sine of this angle is the same as the sine of that angle, because the sine of supplementary angles are equal, so it doesn't really matter. But technically, it's the direction between the direction of, it's the angle between the direction of R, which is going from the rotation axis to the point of action, and the direction of F. And so that's how you calculate it. And so I'll do a few examples with this. So a little more on torques. So there are a few typical examples you'll see. One is, you just have a rotational axis here. Maybe this is the top view of a door, right? And we have a force here, F. And we'll say this is 5 newtons. And then we'll have this distance here, we'll call it our R, which is maybe 1.3 meters. That's a little big for a door, but maybe it's a big door. And so our R would point, from here to here, or something like that. You can just draw it down the middle of the door and say that's our rotational axis. This is the direction of the force. This is the direction of the moment arm. The angle between them is theta. In this case, it's 90 degrees. And so the torque is tau equals R times F times sine of 90 degrees. And so so if you evaluate that, the R is 1.3 meters, the F is 5 newtons. 5 newtons. Hang on a second. 5 newtons. Oh, Jesus. Okay, I'm recording something, honey. Okay, so let's do an example or two of torques. So a typical example of a torque is maybe something like a door. That's just, let's call this the top view of a door, right? And that would be where the hinge is. And so maybe you would apply a force here. And so the distance here, the moment arm would be R is equal to, 1.1 meters. I don't know how big a door is. And maybe I'm applying a force of 2.5 newtons. And so that would be a really tiny force, but it could be. And so this is the direction of my F. This is the direction of my R. And my angle between them is theta. In this case, it's about 90 degrees, typically the way you push on a door. And so the torque is R times F times the sine of the angle. And so that's 1.1 meters times 2.5 newtons times the sine of 90 degrees. And so that's 1.1 times 2.5 is maybe 2.75. Sine of 90 is 1, and so that's 2.75 Newton meters. And usually we would call this a positive torque. We could have another force here, right? We could say, look, there's another force here. Somebody's pushing from this direction. This is, we'll call this F2, even though we didn't call that F1, we'll call that F2. It's acting at this distance, at distance R2. And so, and we'll say this is, I don't know, 0.5 meters, and we'll say this is 4 newtons, right? And then we'll say, so this is the R for this guy. It goes from to where the point of action of the force. I'm assuming this is a thin doorway, right? And so now this R points in this direction, and this F points in this direction. And so I would call this theta 2, and maybe we'll say theta 2 is 45 degrees or something like that. And so then we can calculate the torque due to the second force, which is R2 F2 sine of theta 2, and that's equal to 0.5 meters times F2, which was 4 newtons, times sine of 45 degrees, and so that's 2 Newton meters times 0.7071, that's the sine of 45 degrees, and so this is like 1.414 Newton meters, and I would say this is negative, and so negative because it is clockwise. At any rate, you can see these torques are working against each other, right? This F2 is trying to rotate the door that way, and then F was trying to rotate the door this way, and so they work against each other, and they add just like vectors, and so you can say the net torque is torque 1 minus torque 2, or you can call it plus and just call this guy negative if you want. And so it's 2.5 Newton meters minus 1.4 Newton meters, which is 1.1 Newton meters. So it would end up turning this way, turning in the counterclockwise direction, because this torque is larger than this torque. So that's typically how you calculate torques for simple objects like that have a hinge. There's another example you'll see sometimes. And so let me just grab my eraser, wherever that is. So I might have a round object, say, that's has an axis in the middle. So this is just like a spinning object. This could be a disc, like for a merry-go-round or something like that. It could be a yo-yo where there's a string around it somehow. And so I can apply my force this way. Suppose this is a merry-go-round, right? And there's just one of those park merry-go-rounds, and there's a dad who's exerting a force this way to try to spin it because his kid's sitting on it, right? And so he exerts a force horizontally that way, right? And let's say the radius is 1.5 meters. Notice where the radius meets the tangential force is a 90-degree angle. So this is so this direction and that direction are 90 degrees. And so So a dad pushes a merry-go-round with a 50 Newton force tangent to the merry-go-round. Let me make a capital letter out of that. Has a radius of 1.5 newtons. So what's the torque? The torque is equal to RF sine theta, which is 1.5, sorry, the radius is 1.5 meters. 1.5 meters times 50 newtons times the sine of 90 degrees, which is 75 Newton meters. So that's the torque, right? And now we can ask the question, assuming the merry-go-round has a mass of, I don't know, say 15 kilograms. Let's make it a bigger number. Let's say 25. So, assuming the merry-go-round has a mass of 20 kilograms, what is its angular acceleration? Treated as a solid disk, right? And so, if you remember the relationship between torque and angular acceleration, which is alpha, is torque equals I alpha, or in this case, we want to solve for alpha. Alpha is the torque divided by the rotational inertia. Well, so that means we already have the torque. That's the thing that was 75 Newton meters. Right, and then we have the we have to determine the rotational inertia for a solid disk. It's 1/2 m r squared, which is 1/2 times 25 kilograms times 1.5 meters squared, which is I'll just have to do that on my calculator. 25 times 1.5 squared, 2 is 28 kilogram meters squared. And so that means alpha, which is the torque divided by the rotational inertia, is 75 Newton meters divided by 28 kilogram meters squared, and that gives about 3 2.7 radians per second squared. Sometimes you'll see a string is wrapped around, and so a common problem is to have a string wrapped around something and you're pulling the string. So let me just erase this example and I'll just talk about this, but maybe I won't do another example here. But if you have a round object here and you have a string, and you might pull on this string with a force F, what that can be treated as a force acting at the point where the string comes in contact with the sphere. In other words, or the object, right? The object is round, so the string wraps around it. You can just assume that the string is acting, the force is acting at that point where the contact is made, and so that'll always be a 90-degree angle. And so keep that in mind for problems that have strings wrapped around objects, because often that's the way you start something spinning, like a top or a lawnmower or something like that. You're pulling on a string that's wrapped around something, and so to get it spinning, you do that. So the force just acts perpendicular to the radius at the point where the string comes in contact.